top-class problem solver. The goal of this video is to help us learn to analyze the problem and communicate our solution effectively. A sinusoidal water wave flows past a tracking station from west to east. Measurements taken at the station reveal that the overall depth variation, that is the difference between the maximum and minimum depths, is 4.0 meters, and that the time taken to achieve this, that is from minimum to maximum depth, is 5.0 minutes. At a specific time, taken as t is equal to 0, looking east from the station, the two nearest wave crests are 100 meters and 400 meters from the station. Determine the wave equation y as a function of x and t using the station location as x is equal to 0 and the mean water level as y is equal to 0 as references. The problem-solving method consists of 3 steps. The first step is interpretation of the problem. Then we devise a strategy, and then we execute our strategy. The first step of the interpretation is to identify the concept embedded in the problem. The fundamental concept is sinusoidal waves. So we write this in our solution. The next step of the interpretation is to create the model and represent the model in a diagram. We are told that the wave travels from west to east, so we will make this axis our x-axis with east as the positive direction. We are told also that there is a tracking station and that this tracking station should be the origin of our x-axis. Finally, we are told to make the mean water level the y reference for our coordinate system. So we draw our coordinate system with our x-axis going from west to east. We show that our wave is propagating in the positive x direction. We show our tracking station, this is our little tracking station, placed at the origin of our coordinate system. We indicate the parameters of our sinusoidal wave. These are the amplitude, A, the angular frequency, omega, the angular wave number, k, the phase constant for the wave, which we'll call psi. We also write down a very important equation, which is that the speed of propagation of the wave, which we call u, is equal to the angular frequency divided by the angular wave number. The third step of the interpretation is to extract the data carefully from the problem. We are given 2 sets of information in this problem. Firstly, we're given that at the station, the difference between the maximum and the minimum depths is 4.0 meters. We are also told that the time taken for the wave to rise from its minimum to its maximum depth at that location is 5.0 minutes. We will first transcribe this information to our model. So we have at x is equal to 0, that is at our tracking station, the minimum depth, dmin, and our maximum depth, dmax, indicated along our y-axis. We also indicate the mean level, which is the 0 reference for our y-coordinate. We notice immediately that the difference between dmax and dmin is twice a. We also notice that the time it takes for the wave to rise from dmin to dmax, which here we call tau, is equal to 1/2 of the period of the oscillating wave. So we write all of this under data. We have the twice a is equal to dmax minus dmin, which is given as 4.0 meters. From this we obtain that the amplitude of the sinusoidal wave is 2.0 meters. We then write down that tau, which is equal to 1/2 of the period, is equal to 5 minutes. So then we write down that the period of the sinusoidal wave is 10 minutes, which we translate into seconds. From this parameter, we can obtain our all-important angular frequency omega, and from this we obtain that omega is equal to 0.01 per second. We are also told that at time t is equal to 0, the two nearest wave crests are at x is equal to 100 meters and x is equal to 400 meters. We indicate the location of these two crests on our x-axis. We shall call them x1 and x2. We know that because these are two adjacent crests on the sinusoidal wave, the distance between these two crests is equal to lambda. So we write down that lambda is equal to x2 minus x1, from which we can calculate lambda. And from lambda we can obtain k. Looking back, we see that of the wave parameters, we have now the amplitude, the angular frequency, and the angular wave number. In order to determine the wave exactly, all that is required is the phase constant for the wave. The first step of the strategy is to determine precisely what is required. In this problem, we are required to find y as a function of x and t. The second step of the strategy is to construct the concept map. The concept map relates the parameters that are given in the problem and the required parameter. There are many ways to solve for the wave function y as a function of x and t. We are going to use a way that exploits our extensive experience with simple harmonic motion. First, the wave function y as a function of x of t can be expressed as the simple harmonic motion y of t at any arbitrary point x. So then what we'll do is we'll start off with the simple harmonic motion at the point where we have the most information, that is at the tracking station x is equal to 0. From this, we're going to find the simple harmonic motion at the first crest x1. And then from that, we are going to find the simple harmonic motion at our arbitrary point x. The third step of the strategy is to create an action plan based on the concept map. So the first step of our procedure will be to take the simple harmonic motion at x is equal to 0 and transfer it to our first crest. The second step of our procedure would be to take this equation at our first crest and write down the wave equation for the arbitrary point x. The first step of the execution is to follow the steps of the action plan. Let us first find the equation for simple harmonic motion at x equal to x1. We know the amplitude for the simple harmonic motion at x is equal to 0, and we know the angular frequency for the simple harmonic motion at x is equal to 0. So, as a property of the sinusoidal wave, these are also the amplitude and angular frequency for the simple harmonic motion at x equal to x1. We also know that at time t is equal to 0, the location x1 is at its maximum value. This is in fact why we chose x is equal to x1 for this step of our solution. It turns out therefore that in cosine form, the phase constant for the simple harmonic motion at x is equal to x1 is 0. This gives me then that the equation for the simple harmonic motion at x is equal to x1 is simply a cosine omega t. The second step would be to find y of t at our arbitrary point x. Let us draw a simple diagram showing our x-axis our first crest x1 and our arbitrary point x. We write down the equations for the simple harmonic motion y of t at x1 and y of t at x. We know that y of t at x is identical to y of t at x1 except for the change of phase. We know that the change of phase is proportional to the change of location in going from x1 to x. This is the manner in which the wave is propagating. So we have our parameter delta x, which is equal to x minus x1. We know then that the change in phase is going from x1 to x is equal to minus k, our angular wave number, times delta x. We put in the negative sign because we know that for a wave propagating to the right, as I move towards the right along x, the phase progressively lags. So we now write down our equation for simple harmonic motion at our arbitrary point x as being the equation for simple harmonic motion for the first crest, from which we subtract the change of phase minus k times delta x. It is customary to write the coefficient of x as being positive, so we're going to flip the sign inside of the square brackets. Because the cosine function is an even function, when I flip the sign inside of the argument for the cosine function, I do not change the sign outside of the cosine function. The rest is algebra and substitution. The second step of the execution is simply to write down and highlight your final answer. So here we write our final answer. The third step of the execution is to check your answer. When you check your answer, make sure that you state clearly what is required, that you give the appropriate unit, and that the magnitude of your answer is reasonable. So first we verify that what we're required to find is y as a function of x of t, and this is what we've obtained as our answer. Next we check the unit. So y, position, will be in units of meters, which is what we have here. Inside the cosine bracket, we should have a dimensionless quantity. So we verified that the term inside of the bracket is completely dimensionless. We now need to find a method by which we can determine whether the magnitude of our answer is reasonable. From the start of our problem, we remember that the only parameter that was difficult to obtain was the phase constant. So let's find a method for determining whether the magnitude of the phase constant is reasonable. Let's go back to one of our earlier pictures. We remember from this picture that at time t is equal to 0, we had crests at x1 and then at x2, which is actually not shown in this picture. So x1 was at 100 meters, x2 was at 400 meters, from which we obtained that the wavelength was 300 meters. The first crest was offset from the origin by an amount 100 meters. That is to say, by 1/3 of a wavelength. Now, 1/3 of a wavelength would correspond to 2 pi over 3, which to two significant figures is 2.0. So therefore, we do expect that the actual phase constant for this wave is 2.0. Here once more are the 3 steps of our problem-solving method. Thank you for watching.